over the last few days, we've learned that we represent a vector by a line segment and an arrow on the end of it. If we have two vectors, then we're going to have two line segments with arrows on the end of it. Now, if we want to add these vectors together, what's the goal? We're going to get a right angle triangle. To get that right angle triangle, we have to draw a vector diagram. And a vector diagram is always drawn with our vectors drawn front to back or head to tail. So in other words, if I want to combine these two vectors right here, I could combine them like this. Those are drawn head to tail. Or I could combine them like this. Those are drawn head to tail. I could not do this, because those are drawn head to head, and I could not do this because those are drawn tail to tail. So we got two options, which makes sense, right? 1 plus 2 is equal to 3, 2 plus 1 is equal to 3. It doesn't matter what order we add them in, we just have to add them correctly. Okay, we're adding these two in different orders, but we're still going to add them correctly by making sure that we're drawing them front to back or head to tail. Now my resultant vector, which represents the sum of the vectors when I add them all together, what I get, is going to be that red line vector that's drawn which way? From start to finish. Don't forget to put the arrow on the end of it. Look, I've got two right angled triangles now. Both of these right angled triangles will give me the same value of r. This one might be 10, this one might be 5, this one might be 10, this one might be 5. Anyway, you look at it, you're going to get the same value of r using the Pythagorean theorem. Theta, on the other hand, theta, which is the variable that's going to represent our angle, right here, drawn at the start of the vector diagram, won't be the same. Theta would be, let's say it worked out to be 40 degrees right here. I don't know for sure because I haven't done the calculation, but let's say it was 40 degrees right there. What would it work out to be right here? 50 degrees, right? 90 minus 40 is equal to 50. Both of those would be correct. It's just a matter of expressing what the reference point is. We're going to learn a little bit later on today how we express that reference point. 40 degrees as measured from something, or 50 degrees as measured from something. That's coming today. All right, so how do we deal with this, though, if we happen to have three vectors? Let's say we got one that's this way. Let's make it 20 meters. Let's make one down this way. Let's make it 10 meters. And then let's make another one back this way. Let's make it 12 meters. 12 meters back this way. Is that drawn okay so far, by the way? They're going front to back. I can draw it this way. That's fine, right? My resultant vector will go right here. What's the goal? What's the goal, Liam? Right, sorry? Get a right angle triangle. Do I have one right now? No, so I got to get one. And how am I going to get one? By breaking it up into x and y components. X components, y components, and now let's go through each of these vectors. How much of that 20 meters is on the x-axis? The right-left axis? 20 meters, all of it. How much of that 20 meters is on the y-axis? Well, all of it's on the x, none of it's on the y. How much of that 10 meters is on the x-axis? 0 on the y-axis? Negative, who said negative? Negative 10, good. And on the x-axis, the 12 is? Negative 12, the y-axis is 0. Add these up, we get 8.0. Add these ones up, we get negative 10. We redraw it, 8 to the right. Hey, how did I know that it was 8 to the right and not 8 to the left? Because it's, well, the positive 20 and negative 12 give you positive 8. So the fact that the 8 is a positive value makes it to the right. And the 10 goes downward. I know that because it's a negative value. My resultant vector, drawn from start to finish, is going to be right here. Going to calculate its value using the Pythagorean theorem, and I'm going to calculate the value of theta using the inverse tan of opposite over adjacent. Okay. Now that we got a right angle triangle, it's just like those other two questions we did a couple minutes ago, right? All right. So what if you see a question that's somewhat like the one up on the board, but this 12 meters is not 12 meters to the left, but rather it's 12 meters down here at an angle of 30 degrees. We can still draw a resultant vector from start to finish. That's still a good vector diagram. It's not a right angle triangle. We got to make it into a right angle triangle. But as part of that process, we've got to recognize something. We see something on this diagram right now, and we should automatically think of a 5-word phrase that we said quite a bit yesterday. What is it? I don't like funny angles. I don't like funny angles. I don't like funny angles. So my goal is to get rid of it. Let's take the 12 meters. Let's create a new page here, actually. We had 12 meters with 30 degrees here. Let's complete the triangle by drawing lines, vectors around the 30 degrees. Once you get your right angle triangle here, make sure the 30 degrees is inside that triangle. All right? It is. We're going to label it X and Y. And then we're going to find the value of X and Y by using some trigonometry. Cosine theta is equal to adjacent over hypotenuse. The adjacent side of this triangle is not the hypotenuse, not the longest one, but it's the other one that's touching the angle. So we're going to say cosine 30 degrees is equal to X, or adjacent, over hypotenuse. X ends up being equal to 12 cosine 30. Let's say, let's do sine 90 on our calculator just to double check to make sure we're in degree mode. We are. 12 cosine 30 gives me 10.3923. If you're not sure how I got that, take the 12 up and multiplying and say 12 times whatever cosine 30 is. Sine 30 degrees is equal to y over 12. Y is equal to 12 sine 30, which is 6.0. Now, as far as I'm concerned, this 12 meters doesn't even exist anymore. It's gone. X is 10.39. Y is 6.0. That's good enough. I've just replaced one pain in the butt 30-degree vector with two easier to deal with simpler vectors. So there's a trade-off there, right? I'm replacing one vector with two. So now I've got an extra one, but both of them are easier to deal with than the one that I had. So why do we do this? Why do we calculate the x and y components of that vector instead of just leaving it as 30 degrees? Because if I take this, the 10.39 and the 6.0, and replace this vector with a 10.39 and a 6.0, I got a much easier problem to deal with now. Now I can deal with this the way that I dealt with it before. I can say x components, y components, 20, 0, 0, negative 10. What's the third one? Negative 10.39, 0, and 0, neg 6. Do it exactly the same way as I did it before. I couldn't do that when I had the 30 degrees in there, right? Now I can. There's one extra vector, but it's an easier one to deal with than what I had before. More work is better if it's easier. We got a little bit more work to do here, but it's easier, so it's better. All right? Yesterday, we were working on a worksheet. I signed up to number 13 for homework on that worksheet. I want to take a look at maybe a couple of those, one or two of those questions, and then maybe do one more example, say like question number 14 that I asked you to take a look at yesterday, and then finish off with leaving you guys with number 15 and 16 to work on yourselves. Let's just do number 13 here. Let's just do number 13. Funny angle. Our response to that funny angle is we don't like it. We don't like funny angles. So we get rid of it. We deal with it here, right? We got a triangle that's built around the 30 degrees. Make sure the angle is inside that triangle. This is x, this is y. We're going to say cosine 30 degrees is equal to adjacent, not the hypotenuse, but the other one that's touching the angle, adjacent x over the hypotenuse, which is 80 meters. X is equal to 80 times cosine 30. When I do that, 80 times cosine 30, I get 69.282. For the y component, I'm going to use sine. Sine is opposite of hypotenuse. Sine 30 is equal to opposite, the y component, the one that's not touching the angle, over 80. Y ends up being equal to exactly 40 meters. There we go. Now, this is part of a bigger problem where we had to add vectors together. We just replaced the 80 with 69.282. And 40 meters over here. And then we pretend this 80 meters doesn't even exist. It's dead to us. All right. Let's take a look at number 14. We'll do that as a group, and then I'll leave you with 15 and 16 to work on yourselves here. Question 14. First thing I noticed here is that I got a funny angle. And my response to that is, I don't like funny angles. I don't like it. So I'm going to take it off to the side and get rid of it here. I got 10 meters. I got an angle of 30 degrees here. And I got to make sure that my triangle that I'm building here is built around the 30 degrees, so that the 30 degrees is inside that triangle. This is x, this is y. Let's say cosine 30 degrees is equal to adjacent. Which is the adjacent side, x or y? X, because it's touching the 30, and it's not the hypotenuse. Sorry, touching the 10. Touching 30, and the 10 is also touching the 30. That's the hypotenuse. So I get x is equal to 10 times cosine 30, which is 8.66025 meters. We're going to say sine 30 degrees is equal to y, that's the opposite side, over 10, which is 10 sine 30, or 5.0 meters. So now it's as if this whole 10 meters doesn't even exist, right? It's gone. Now, let's replace this up here with an 8.66025, and this one down here with a 5.0. And then let's just scratch this out. Why am I not taking into account the original 10 meters? I am. I'm just taking into account as the components of that 10 meters as opposed to the 10 meters itself. So let's do our whole x and y thing. Let's say 8 meters, 0 meters, 8.66025, and 0. And the last one would be 0 and negative 5. Add these up, 16.66025. And negative 5.0 meters. 16. How did I know that 16 is to the right? Because it's positive. And the 5 is down because it's negative. There's my resultant vector right there. I can find it by doing the Pythagorean Theorem. And theta, always measure the start, the inverse tan function. Opposite over adjacent here, right? What's opposite, 16 or 5? Which one's not touching the theta? The 5. So opposite over adjacent, 16.66025. Okay, let's figure this out. We're going to say 16.66025 squared plus 5 squared. We're going to square root that. 17.4, which I think we're going to round to 17 meters. And theta, last thing I want to do with you here today, theta is the inverse tan function. I'm just going to hit sine 90 to make sure I'm in degree mode. Yep. The inverse tan function of opposite over adjacent. $16.7, 17 degrees. 17 meters at 17 degrees. Make sense? Now, I promised you that I was going to show you that frame of reference thing. And how do we express relative to what? Tell me the two directions I'm going in this diagram. Like, look at the blue vectors. Tell me the two directions I'm going. You wouldn't say southeast, because southeast represents exactly 45 degrees, but you're on the right track. We're going south and we're going east. Yeah, it would be south of east. You're going to say south of east. Look at this. We went east, then we went south. We went south after we went east. So we're just going to replace the word after with of. South after east or south of east. That make sense? Now, if you had drawn it the other way, like this, that would have been correct. You would have gotten a value of r of 17 meters, but you would have gotten a value for theta of 73 degrees. It would have been correct because it would have been 73 degrees south of east. It would have been 73 degrees. We went south, then east, east after south, or east of south. Now you can see how we can express two different angles meaning the same thing. Kind of like that example that I've been using for the last few days. 1 north of the front of the room, 7 south of the front of the room. Okay, both mean exactly the same thing. Okay, your homework for the weekend is simply going to be to finish up this worksheet, which is question number 15 and 16, please.